In our next example, we have a car driving up a hill at 60 miles per hour. And to keep things a little bit simple, well, in a way, theoretically anyway, there's not going to be any friction, so no energy loss due to friction. Now, of course, in the real world, that's impossible because you can't drive up a hill if there's no friction. The car will not go anywhere. The tires will simply spin out and the car will just slide down the hill. So just assume that we ignore that little fact. And let's say the hill has a steepness of 6%. The Mazda car, 2,000 kilograms, wants to drive 60 miles per hour. How much horsepower does it take? And then again, assuming that no energy is lost in the internal workings of the engine itself. So whatever the engine puts out, it uses all of that energy to go up the hill, which of course is also not true. Typically a car only uses about 25% of its energy that it puts out. All right, so how do we go about doing that? First of all, I think I want to go ahead and turn this into an angle. So when we talk about the road having a steepness of 6%, that means for every 100 feet that you drive along the horizontal axis, the road will go up by 6%. So it's basically a 6 to 100 ratio, which means that if it's a 100% hill, then it would be 100 to 100, which gives you a 45-degree angle. So degrees and percentages are not the same when it comes to the steepness of a road. All right, so if we take the arctangent of the opposite over adjacent, we can actually turn that into an angle. So for example, theta here would be equal to the arctangent of the opposite side over the adjacent side. And let's see what that gives us. So 0.06, take the arctangent of that, that's 3.434 degrees. 3.434 degrees. All right. Now 60 miles per hour, let's convert that to meters per second. So we take 60, and we first have to convert that from miles to meters. So 1 mile is 1,609 meters, and now from hours to seconds. So we have seconds at the bottom, hours at the top. 1 hour is 3,600 seconds. Notice that the hours will cancel out and the miles will cancel out. We're left with meters per second. So we take 60 times 1609 and divided by 3,600, and that gives us 26.8 meters per second. All right, so now we have some better units to work with. Now, we can say that power is equal to work over time, but it can also be defined as the change in energy over time. The change in energy over time. Now, notice that the car is not gaining energy as far as kinetic energy is concerned because the car is driving at constant speed, 60 miles per hour. But the car is gaining height, so the energy increase is the potential energy increase of the car. So we can say that the change in energy is equal to the change in potential energy over time. And potential energy is, of course, mgh, so it's equal to the change in mgh over time. And well, mg is constant, so this is equal to mg times the change in the height over time. So that would be the rate at which the car is gaining height. So can we translate the speed along the hypotenuse here into the speed along this vertical axis? So this would be the dh dt that we're looking for, or the change in the height over the change in time. Now, no, I didn't use a delta in front of the t, but I can go ahead and do that to make it a little bit more understandable. This simply means the amount of time elapsed during that interval. So how fast we're gaining height per unit time, how are we going to relate that to the dx dt over here? The x dt along the road, which is the change in x over the change in time. So we can see that that would be a ratio of the hypotenuse to the opposite side, and of course the relationship between the hypotenuse and the opposite side of the angle theta right here, because here we can say that theta is equal to 3.43 degrees. Let's just round it off to three numbers here. Then we can say, okay, the sine relates that. So we can say that the sine of theta is equal to the ratio of the opposite side over the hypotenuse, which means if we solve this for the opposite side is equal to the hypotenuse times the sine of theta. And of course, the opposite side is represented by delta H delta T, and the hypotenuse is defined by delta X delta T times the sine of theta. And of course, the delta x delta t is simply the velocity of the car, which would be 26.8 meters per second. So what that means now is that the power required here is equal to mg times delta h delta t, which is equal to delta x delta t times the sine of theta. So we'll replace delta h delta t by what it's equal to, delta x delta t times the sine of theta. And of course, delta x delta t, again, that's simply the velocity of the car. So plugging everything in now, we have a mass of 2,000 kilograms. The acceleration due to gravity, 9.8 meters per second squared. So here we have the mg. The delta x delta t is the velocity, 26.8 meters per second. And finally, the sine of theta would be the sine of 3.43 degrees. All right, now we're ready to go ahead and figure out how much power that car requires to gain that height over that amount of time. Okay, so we have 2,000 times 9.8 times 26.8 and times 3.43, take the sine of that, equals, and let's see here, this requires 31,427 watts. Of course, we usually don't talk about watts in cars, we talk about it in terms of horsepower, so let's convert that to horsepower. To put horsepower at the top, watts at the bottom, 1 horsepower is 746 watts. So let's divide this by 746, and that would require 42 horsepower. I say, whoa, that's easy. Any car can do that. Even my car that only has 106 horsepower should easily be able to drive up that hill at 60 miles per hour. But we forgot one thing here. Most cars don't use 100% of the energy output of the engine to propel the car. A severe amount of energy, a large amount of energy is lost due to friction and wind resistance and all that. So typically we're talking about a car maybe only 10-20% efficient. So at 10 or 20% efficient, it would need anywhere from 210 to 420 horsepower to drive up that hill that fast. And so not all cars can do that. But for our sake here, this is a good a good problem to start with, ignoring friction, ignoring efficiency, and simply saying that the power is equal to work over time or change in energy over time, and then we have to define what that change in energy is, which in this case is the change in potential energy, and then we have to convert from the delta x delta t to delta h delta t so we can work out the problem. And that's how you do that.